Okay, good afternoon, everyone. Let's get started. So first, a kind of reminder, our homework 2 I believe it's due on this Friday. No programming assignments. I think it's about 7 or 8 problems, and just check your understanding of graphic model and some product algorithm. You can just follow the example we explained in the class. It should be pretty straightforward. But please, if you don't have any, if you haven't started yet, please start right now. It's also not very easy to finish it 3 hours before the deadline. And again, please take advantage of the office hours. Our office hours are pretty empty in the past few weeks. Yeah. Okay. So today we're gonna wrap up variational inference. So in the last lecture, we introduced another type of variational inference algorithm, which we call local variational inference, right? So the different from the global variational inference, the local variational inference aims to introduce some approximation to the factors in the joint probability, right? So we know that this framework is the global variational inference, where you introduce some approximate posterior distribution, which we denote by Q of W, right? We maximize this variational evidence lower bound, which is equivalent to minimizing the KL divergence from your approximate posterior to the true posterior, right? So we mentioned that in particular cases, like even maximizing this lower bound won't be feasible. The reason is mainly from the factors inside this joint probability P of TMW, right? So in general, if it is written as a product of a set of factors, well, I would write it as T and WA, something like that, right? So if the factor it may correspond to some prior or correspond to some conditional distribution, it's so difficult to compute. Then you take expectation over this log fraction, it even doesn't give you any closed form, right? That will bring some challenge in the optimization, right? So the idea of the local variational inference is that, okay, right now we introduce some approximation form of this factor, right? Typically, we can use some convex conjugate to introduce some lower bound of this guy, like something like lambda transpose, maybe I should use C, right? The C transpose some W subtracted by G per C, some function like that, right? So if you know the convex duality, or you can extract out some relevant terms inside this factor, which is convex, you can apply the convex duality. And then you can see that the related random variables WA in the lower bound is just a linear term, right? It's just in a linear term that will usually bring extreme convenience in maximizing this lower bound. Right? So we use the logistic regression as an example, but due to the time limit, we won't be able to go through every detail again, right? But just want to remind you some general framework where, like, the local variational inference is that, okay, we're going to introduce some relaxation, easy form of the lower bound over those difficult factors in a joint distribution, so that we can construct a lower bound further on the joint distribution, right? Then we just substitute this new lower bound of the joint distribution for the joint distribution in the variation evidence lower bound, then you maximize the bound. That's it, right? But there's no free lunch, right? You introduce this easy form of lower bound, you usually have to introduce additional parameters. Here we denote these additional parameters by C, which we call variational parameters, right? So you not only need to maximize this lower bound, although the form usually becomes much easier, but you have to optimize both the approximate posterior Q of W. Also need to optimize this additional variational parameter C to tighten the bound, right? That's the idea. So actually you kind of augment your objective function by introducing some additional parameters, right? The benefit is that, okay, through this augmentation form, your whole optimization, the computation is much easier. the cost is that, okay, you have to optimize additional parameters. Right? So that's the kind of a trade-off. And then we introduce the this alternating updating procedure, right? In the logistic regression framework, where we alternatingly update this Q of W, right? The original posterior approximation of the true posterior, and also update the variational parameters specific, right? To tighten this bound. Right? So the step where we update the approximate distribution Q of W, we call E step. It's kind of like consistent with the standard EM algorithm. Right? Then the step we optimize the variational parameters to tighten this bound, we call it as M step, right? This meaning that we maximize the lower bound with respect to the C. Right? So you can see that there's a kind of a very similar EM cycles, like as in the standard EM algorithm we discussed before. Right? The only difference is that your objective function has been changed, right? Now it becomes the original lower bound of the evidence, right? And your Q of W is not the true or exact posterior distribution. It's just to optimize this approximation to the true distribution, right? And in M step is not. This is not the model parameters. It's just some additional parameters to ease the bound. And then we can extend a case where we include both the model hyperparameters, like which we only need some point estimation, and some variational parameters, right? You can still cast them into this variational EM procedure where in the E step, we update or optimize this variational posterior Q of Z. In the M step, we jointly update the model parameters theta and also the additional variational parameters, if any, right, to maximize the bound. Okay, any questions so far? We just do a quick review of what we have discussed last week. Okay, great. So the last thing we want to talk about is some graphic model into view of the variational inference. Right? So we call it variational message passing. Right? So previously we talked about, okay, in the graphic model, if your variables, graphic model are discrete, how do we do some sum product algorithm or max sum algorithm to do some kind of inference, right? So actually we can extend this framework or this message passing scheme into the variational inference framework. Right? So here we consider some Bayesian network. Of course, it can be any other framework, like undirected graphic model, doesn't matter, right? And we're assuming mean field approximation. What is mean field approximation? I heard that. Can you speak a little bit loudly? Yes, yeah. Mean field means that, okay, I'm going to assume my approximation is factorized over the random variables in the graphic model, right? And here we're assuming my graphic model, say each random variable we denoted by x1, x2, x3, x4, x5. So I'm assuming my posterior of this 5 random variable is fully factorized. Right? That's my assumption. Right? And then we can look into the update, namely the mean field variation update in the graph. Right? How does the graph structure can decide the mean field update, and how does this update reflect some kind of message passing protocol? So this is a standard mean field variational inference update, right? We discussed previously. So if we want to update the posterior regarding variable xj, right? Q of xj, it is proportional to, we're going to first take the log joint probability over all the variables, right? Then we take expectation under the current variational approximation over all the variables other than G. Right? That's what this X not G means, right? It just means X excluding XG, right? We just take expectation of the log joint probability under Q X not G, right? You know that it will become some function of XG only, right? Because all the other variables other than XG can be marginalized out, right? And then you take exponential, you do the normalization, you get your mean field update of QXG, right? And in the mean field version inference just means, okay, you just cyclically update each of QXG, right? You update QX1 while you're fixing QX2, X3, X4, and so on. Then you update QX2 while you're fixing QX1, QX3, QX4, and so on, right? So let's see. Let's see in the general case, right? We know your joint probability is something like this, right? P of X is product over a set of factors, right? FA, XA, right? So it's possible that not every factor in the joint probability will contain XJ, right? It is possible. So if a factor doesn't contain XJ, is not related to XJ, what will happen in the variation update about QXG? Any thought? Let me use a very simple example to explain this, right? So suppose I will have two variables, right? I can write it as P of X1, P of X2 given X1, right? So now if I want to update Q of X2, right? So which factor has nothing to do with X1? The prior, right? The P of X1, right? P of X1 is constant to X2, right? Doesn't contain X1, P of X1, right? And let's see if we update this variational posterior over QX2, right? You see that PX1 can be ignored. Okay, let's just apply this, right? Just apply the rule here, right? So according to this variation update rule, mean field variation update rule, right? So QX2 is proportional to, we're gonna first take a logarithm of this joint probability, right? Which is PX1 plus P of X2 given X1, right? And then you're gonna take expectation of QX1, right? You're gonna exclude X2, right? Then you take exponential, right? Then you do normalization. So you can see that this guy actually is constant to X2, right? Log P of X1, or of course you can do the expectation over log PX1 under QX1. You can do that, but actually it has nothing to do with QX2, right? Because it's constant. If we do the normalization, this guy will be just cancel out, right? So that means if you really do the update of QX2, you only care about the factors that contain X2, right? Because those guys are form the final function, like final function of X of the target variable, right? For all the other variables, they're just constant, right? If you do the normalization, they just cancel out. So that means it is proportional to the exponential of E Q of X over log, sorry, QX1 log P of X2 given X1 only, right? They're the same. Does it make sense? Right? Well, actually, we never need to care about those terms that do not contain X2. right? Any question? Yeah, let me know if you feel uncomfortable about this. Does it make sense? Right? If you, I mean, let me repeat this in case that you still like feel uncomfortable, right? So if you do this, right? If you do this following the rule, right? Exact rule, right? If you're updating rule, right? So you can see that this guy essentially is you take exponential of expectation over qx1 log p of x1 times some constant, right? Times some constant, right? This c actually is exponential of e q x1 log p of x1, right? And this has nothing to do with x2, so we can view it as a constant. Does it make sense? Right? And then, as we said, like this is not the true distribution, right? You have to do some kind of normalization, right? Right. When you do the normalization, well, you know you have to integrate out x2 again, right? So this c is just moved out. It's a common factor. If you write it in more detail, z should be some c and times exponential of this guy, eqx1 log p of x2 given x1 and d x1, right? So you can move c out, right? Because c has nothing to do. C has nothing to do with sorry, it's x2, right? Nothing to do with x2. Right? You should just move it out. Right? So you can see that when you divide by z, like c is both in the numerator and denominator is just cancel. That's why actually when we do the mean field update, we just need to take out all the log factor terms that contain the target variable. For all the remaining factors, those remaining factors do not contain the target variable at all. We can just throw them out. Does it make sense? Right. If you still feel like uncomfortable, you can just follow the simple example we discussed. Right, you get to know that. Okay, so then, given this observation, right, we know that actually when we do the variational mean field update, we do not really need to take expectation over the log whole drawing probability. We just need to take out all the log factors, meaning those conditional probabilities that contain xj, right? So then, when we consider a Bayesian neural network, right? You know, the Bayesian neural network, those factors in the drawing probability are just a set of conditional probabilities, right? So only to look at the log conditional probabilities, where in those conditional probabilities, xj is either in the conditional part or as the target variable part, right? So either the parent or the child. Does it make sense? It's just part of them, right? So you just need to take the expectations on these relevant conditional probabilities under the variational posterior over the variables inside those conditional probabilities, right? So now, those variables inside the conditional probabilities that contain xj will be the Markov blanket of xj. Right? If you could recall, right? We mentioned that, okay, in the Bayesian network, conditional on what set of variables, the remaining variables will be independent to xj. They are the Markov blanket of xj, right? And those Markov blanket contains all the variables in the conditional probabilities that contain xj. Like for example, like p of xj given x1, x2, right? x1, x2 are the parents in this conditional probability, where the child xj, so x1, x2 is inside the Markov blanket, or x3 given xj, xj is parent, x3 is a child, and x3 is also in the Markov blanket. You just enumerate all the conditional probabilities in the joint distribution which contain xj and take out those variables which also coexist in those conditional probabilities. They form a Markov blanket. Okay. And then your variation update about Q of xj, I'm going to use, is just to take the log probability, log conditional probabilities that contain xj, then take expectation under the variational posterior of the Markov blanket of xj as a subset of variables in this graphic model. You can view it as neighborhood of xj, right? And then you take exponential, then normalize, you got qx. Does it make sense? Okay. Does it sound reasonable? But again, I mean, if you are struggling with a little bit more details on that, it's totally fine. Like we won't be able to capture every detail you want to discuss, but just keep in mind, like we'll actually do the variation update for every variable in your Bayesian network. You only care about the variational posterior of the neighbors of xj. That's it. The neighbor of xj in the Bayesian network is called Markov blanket. And through this update, right, we know that this update is based upon the neighboring nodes of xj, right? This actually reflects a kind of message passing for total. I will see this. I will see this. So for the ease of understanding, we're going to convert it back to the factor graph, right? We know we talk about the graphic model, the message passing. We'll talk about how do we send message from factor node to the variable node, send message from variable node to the factor node, right? So for this guy, like for this Bayesian network, we kind of use a similar structure to tell what's their difference and what's their commonalities, right? So we know that this this represents a factor. You can view this as some conditional probability or like x1, x2, something like that, right? And this corresponds to another factor, right? This corresponds to another factor, right? So if you convert it to a factor graph, it'll be something like this, right? It's xj and like for simplicity, that just write those neighbor nodes to xj is x1, x2, x3, x4, x5, x6, right? So those factors obviously corresponds to some kind of conditional probabilities. So, so in this factor graph, right? This factor graph, the first difference from the previous graph is that we are assuming that x1 to x5, x6, and including xj are all continuous random variables. They can be continuous random variables. There's nothing to worry about, right? And then the first is that if we want to send a message from a variable node to a factor node, right? So in the variational inference framework or variational message passing framework, the message is simply your variational posterior. So basically, you send the same message to every neighboring factor, which is just your current variational posterior. This is not like in the previous discussion where the variable node, the message sent from a variable node to a factor node is a product of message from other messages, right? From other neighboring factors to this variable node. Now here we're assuming that, okay, each variable send exactly the same message, which is its current variational posterior to every neighboring factor. This is the first protocol. We send, like say, the message sent from any variable to any its neighboring factor right? It's simply the current version posterior. Right? And then the problem is that how do we compute the message sent from a factor node to a variable node? Right? This actually is reflected from this mean field version updating rule. Right? So let me just write down this rule and then we just take a look, right? So, so let me take this as F1, right? So if we want to look at the message sent from F1 to XJ, right? What are we gonna do is that we take logarithm of the factor, right? Which is X1, X2, and XJ, right? So this is a conditional probability, right? F1 essentially is a conditional probability of xj given x1, x2, right? And here for simplicity, I just denoted by x1, right? And then I'm gonna integrate the message sent from x1 to f1 and x2 to f1, which we know they are qx1 and qx2, right? So how do we integrate them? We do the expectation. Okay. We just do the expectation of the log factor under the incoming message to f1, which is qx1 to x2. Right? And then it's not finished yet. Then we take exponential. Right? And then how do I aggregate the message from all the neighboring factors to a qxj? It's very similar, right, to the message passing protocol introduced before. We just multiply them all together, right? We just multiply all the messages sent from its neighboring factors together. And then we take some normalization. Then I got my qxj. That's it. Does it make sense? Right? I mean, I'm lazy. I do not want to write out the message sent from this factor to here, but you can see it is log some conditional probability and take expectation under x3 and x5, right? You take exp, and this guy is the log conditional probability here, right? And take expectation under x6 and x4, right? Take exp, you multiply 3 exponential terms together. That's where you get this, right? And then you do the normalization. So this is slightly modified message passing protocol is called a variational message passing. So hopefully to give you some kind of thinking or enlighten you to think about. Actually, the message passing protocol can be different, right? So this is just another way of doing message passing, right? And third way of doing that is called expectation propagation, which we don't have time to introduce in this class, but it's just another message passing protocol. Right? And this message passing protocol can be justified as maximizing some variational lower bound, right? And if you change to another message passing protocol, which is called expectation propagation, it can be justified optimizing some energy function defined on the graph. Okay. Any questions so far? Okay. So the variational message passing protocol reflects the fact that given graphic model, the mean field variational updates only requires a local computation on the graph, meaning that only requires neighboring nodes variational posterior, and then you can compute the result according to the local structure of your graph. Okay, so now we have finished the introduction of the variational inference framework, right? Although I mean, version inference framework is kind of a standard framework of probabilistic inference nowadays, right? And there are like numerous techniques and variants are proposed every year. Like recently, people are proposing like stochastic version inference, right? Using stochastic optimization to overcome like intractability of the optimization issue, or they try to expand the family of the variation approximation distribution by using some kind of like random variable transformations, right? If you have heard of this called normalization flow, some places it's called gradient flow, whatever, right? So, but all the basic frameworks and techniques actually have already been included in our discussion. So whatever variational inference algorithm, they're always trying to maximize some variational lower bound. That's all their trick. The only difference is that, okay, how do you design the family of Q of W? How do you do the optimization, right? So we can consider a relaxation of that, or we can consider stochastic optimization, right? And so on. So regarding this topic, right, throughout our discussion, we expect you to know all those list of physics, right? So what is YAM algorithm? So what's the E step? What's the M step, right? And how do we motivate the variational inference algorithm according to the YAM algorithm? So YAM is actually a very ideal algorithm, which assume that given the model parameters, so you're able to exactly compute the posterior distribution of the hidden variables, right? In most cases, it won't be feasible, right? That actually motivates the variational inference, right? And the variational inference essentially leverages structure derived from the Jensen stability, where you can decompose the log evidence as a summation of variational lower bound and the KL divergence. And so that means you maximize the variational lower bound, it is equivalent to minimizing the KL divergence. That's the whole logic of variational inference, right? And you should know what is YAM algorithm steps, what is global variational inference, what is mean field update, and how do we perform general update in the exponential family, what is local variational inference, right? And what is the key idea of that? What is strategy? And how do you use convex conjugate to construct the local variational inference, local variational evidence lower bound, right? And how does the variational inference, especially mean field update, relate to message passing in the graphic model, right? And eventually, we hope you will be able to derive and implement variational inference by yourself. Okay, any questions so far? Okay, so the next, we're going to spend the remaining of today's lecture to give a concrete example of variational inference application. Okay? So this leads to a very successful work 19 years ago, right? 19 years ago, and leads to like numerous papers, right? It was being a hot topic for, I guess, for 10 years. And it's also widely used in industrial applications, right? And it is this paper kind of like a popularized variational inference. Right? So honestly, it is through this paper I learned what is Bayesian inference and what is idea of variational inference. This is called latent directly allocation, right? We briefly mentioned that before, right, when we introduced the basic distributions. Today we're going to use this example as a concrete model and concrete example to showcase how variational inference is applied. So what is directly application, right? So we're going to introduce what's the motivation, what's the model and structure, and we're going to introduce the variational inference framework for model estimation. So what is directly latent directly allocation? So we can view it as a classical text mining model. So in the text mining, or even information retrieval, like in Google, there's a very, very important topic or task is to extract topics from documents. Like, Google, the major profit of Google is to sell its keywords, right? And sell its keywords as the suggestion of the advertisement words, right? So that people search that keywords so that they can match the right advertisement and attract the users to click into that or buy it, right? And the keywords can be viewed as kind of topics. So if you're interested you can take a look at this link, right? We're not gonna click this link, right? It just introduced how this model, this latent directly allocation model, is applied in industrial applications. But to see that this is a very broad use in all kinds of text mining and related tasks like information retrieval, text classification, advertisement, keywords extraction, sentimental analysis. Also, it's a good example to study based on. So, in many places, it is equivalent to these two models are equivalent. Like latent directly allocation, when people refer to that, this means they're talking about topic models, meaning how do we automatically extract topic words from a collection of documents. So here is one example of running a latent directly allocation model on some news documents, right? So those different colors represent different topics. Right? So here topics means what? A specific topic means that, okay, a set of a specific distribution over the words. So basically you can consider like you have a dictionary of words, right? It might contain 1,000 or 10,000 words. And then when I assign distribution over those words, it's like a very high dimensional categorical distribution, right? So the words which occupy the largest probabilities in that distribution actually represents what this topic means, right? For example, this LDA model extract the set of words, right? In this red topic, right? You can see the top ranked words, which mean that they take the largest probabilities in this categorical distribution over the dictionary, are new, film, show, music, movie, musical, actor, York, opera, theaters, actress, those kind of stuff, right? So those actually reflect meaning they're talking about arts, right? It's about either, music, movie, or painting, those kind of stuff. If we take a look at another topic distribution, right, which can be viewed as budget topic, how is this budget topic reflected? Right? It's reflected by the top ranked words, which take the highest probability in the distribution, right? You can see that the top ranked words, right, include million, tax, program, budget, billing, federal spending, money, Congress, those kind of stuff. Right? So you can see they're reflecting something planned for money. Okay? And similarly, like children, women, people, that's another distribution of the words in your dictionary, right? The highest the words which have the highest probabilities reflect the meaning of that topic. Right? So this shows that the LDA, when you feed a collection of documents to this model, it can automatically infer a set of different word distributions. And each word distribution reflects a particular topic. Right? And this topic is represented by top ranked words who has the largest probabilities in the distribution. Does it make sense? So this is our original paper, right? I put the link in the slides. So if you're on time, you're interested, you can take a look at that. It's very good. I mean, not only a very good paper to introduce this topic, extraction framework, but also very, very good tutorial about the evaluation inference. So in my grad, when I was a grad student, there's not a very good tutorial introducing those techniques, right? So we learn those techniques through reading the papers. And this is a very good paper telling you how to apply evaluation inference. Okay, so now we talk about, we first introduce this LDA model. Right? So LDA model, first, it is a probabilistic model. Right? It uses a probabilistic framework to model the generation of a collection of documents. So you can view like, okay, I'm gonna kind of like a Bayesian law. I'm trying to use my probabilistic procedure to compose every document in my document collection. So my composing procedure is summarized as follows. So first, we assume that we have k topics, right? You need to tell, okay, how many topics you want to generate, according to which you want to generate documents. And then we're gonna first sample k topics, meaning k word distributions. So we're gonna have k word distributions, right? So remember, each word distribution is a categorical distribution, right? Each word can be viewed as a token. Right? So suppose you have a large dictionary of tokens, right? And then you have to sample the distribution, several distributions over the same dictionary of tokens. Right? And each distribution represents a particular topic. And then we're going to use these topics, this k sample topics, to generate every document in the corpus. How can I do that? Right? For each document, right, before we sample or generate each word, we're going to first sample a topic mixture distribution. So basically, a document might contain multiple topics, right? But it might largely bias on topic 1 and lessly involve topic 2, right? Never talk about topic 3, right? So in this way, like to express this kind of flexibility, we're going to sample a topic mixture distribution. This distribution is a categorical distribution, like over the k topics. So you can view like, for example, in document 1, my sample of the topic mixture could be 0.6, 0.2, 0.1, 0.1. I suppose my k equals to 4, right? So this just tell that, okay, in this document, I believe there are 0.66% of the words are talking about topic 1, like sports, right? Only 20% of the words talk about topic 2, like entertainment, like politics, right? And maybe 0.1 and 0.1, 10%, and 10% other words talking about topic 3 and topic 4 respectively. And once we are given this topic mixture distribution, we're going to use that to generate every word in the document. How can we generate that, right? So we're going to first sample the index of topic according to this topic distribution, and then we retrieve the corresponding word distribution of that topic to sample the word. And in this way, we generate every word in a document. And when we finish generating this document, then we sample or we'll generate another document. To generate the second document, again, we're going to sample another topics mixture distribution, which might be different, right? It could be 0.1, 0.1, 0.6, 0.2. Right? It could be under another topic distribution. And under that topic distribution, I'm going to sample the topic for every word and pick up the associated word distribution to generate the word. Does it make sense? So now let's dive into the details. This is a graphical model representation of the latent directory allocation model. Right? As we mentioned, right? So first, we need to sample big K topics, right? Each topic is a distribution over the words, right? Suppose our dictionary consists of V words. That means each topic is a distribution over the V words, right? So it's a categorical distribution with cardinality V, right? And you're gonna generate. So here, beta K represent the topic distribution for topic K, right? So because you have a big K topics, you're gonna sample k such probability vectors. And once we have that in hand, right, we're ready to use these topics to generate document, right? And then we look over every document, right? So this plate means that we're going to generate a big M documents, right? So to generate each particular document, right, first we're going to generate or sample a topics matrix, which indicates how much portion of the words are in topic 1, how much portion of words are in topic 2, how much portion of words in topic 3, and so on, right? So we denote this topics matrix by theta n. Again, this is a categorical distribution, right? In other words, this is a probability vector multinomial distribution. And then under this topics matrix, we're going to sample every word in the document, right? So for every word, right, we're going to first sample the specific topic on this word, right? How do we sample that? We're going to sample Z and J. Z and J just means the topic of jth word in document N, right? It is sampled from a categorical distribution parameterized by theta n. Right? So remember, theta n is its categorical distribution, right? It could be 0.1, 0.3, 0.6, 0.0, right? So then every time you're going to sample either topic 1 or 2 or 3 or 4 according to this probability vector. Once you identify the topic of this word, say the topic of this word is 3, right? It's topic 3. Then I'm going to retrieve the word distribution of topic 3, which is denoted by beta 3. Right? Remember, it's a vector of probabilities over the words. Then you sample a word according to the topic distribution regarding a word. Does it make sense? Any question? David? Yes. 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 So as we mentioned, right, in a probabilistic model, you always assume how the data is generated, right? It is generated by some sampling procedure, but once you observe all those words, right, your task is to infer what the latent variables are. You just sample, right? So here the latent variables includes, okay, what is the topic distribution? What is the topic mixture for every document? This one? This one? This one? Yes. Yes. So, okay, maybe we'll look at this one. It is easier to explain the whole model, right? So first, don't consider like this generation procedure like human composing the paragraph. It's not like that. It actually uses a very, very simplified statistical model to model how these words are sampled. Actually, it makes too much simplification. Like it ignores like strong dependency between those words, right? They're assuming that, oh, given the topic and given the topic mixture, those words are independent. But actually, it's not. I have to point out that. So it's definitely right to see like this model is oversimplistic, but it's good to we're good. No, in many cases, even uses oversimplistic generation procedure is enough for us to extract critical topics from document. Okay, so then let us say use this paragraph, right, to explain or to map the sampling procedure in a latent directly allocation model, right? How can I do that, right? So first, right, remember we said that in the first step, we're going to sample k topics, right? So here, suppose we got k equals to 4, right? Of course, we don't know what's the meaning of these 4 topics. This meaning are reflected when we do the inference. You know, okay, it reflects by arts, badges, children, and education. At the beginning, you just assume, okay, there are 4 topics reflected in this document, right? So we're going to first sample 4 distributions over the words. So over the same set of words. Maybe I have like 10 to the power of 4 words, right? So this distribution is over this 10 to the 4 words. It's a very high dimensional categorical distribution or multinomial distribution, if you like. Right? So this could be like, say, word 1, word 2, word 3, until word 10 to the power of 4. I mean, in the first topic, distribution, it could be 0.1, 0.001, 0.002, blah, blah, blah. And the second one could be 0.04, 0.003, 0.10, and so on. And third one could be 0.001, 0.0009, and so on, right? So anyway, each distribution is represented by a long probability vector, and the summation of those probabilities are 1, right? It actually corresponds to a multinomial distribution over this 10 to the power 4, or 10 to the 4 words. Does it make sense? Right? And then we model how we sample or generate this specific paragraph. How can we do that? First, we're going to sample a topic mixture vector for this document. The topics mixture vector is actually another multinomial distribution, which is just the 4-dimensional, right? Because here k equals to 4, right? I just random write something like, maybe it's just 0.3, 0.2, 0.1, 0.4, right? So this is another multinomial distribution, right? Theta here is a vector of probabilities. Their summation is 1 again. I wouldn't say it's hyperparameter. It's not hyperparameter because we will theta as a random variable as well. Right? So this mixture just tells us, okay, I believe the word I'm going to generate will contain 30% of words for topic 1, 20% of words for topic 2, 10% words for topic 3, and 40% words for topic 4, right? And then we're going to generate word by word for this paragraph. We're going to do that. So first, how do we generate the? First, we're going to sample a topic indicator for this word. How to sample it? Right. It is sampled from a multinomial parameterized by theta. So you know that it will give you either 0, 1, 0, 0, 0, 1 hole including, right? 0, 1, 0, 0, or 0, 0, 1, 0, or 0, 0, 0, 1, right? It's just the index telling you which topic this word is going to belong to. Right? Suppose my sample ZN1, the topic index for this word is 0, 1, 0, 0, right? Meaning that I believe, or my sampling machine tells me, okay, I pick up topic 2 for this word, and now how do we generate a specific word? I'm going to look up the topic distribution, which we just generated, because we believe the first word will be generated by topic 2. We're going to look at the second topic distribution. I use that distribution to sample the specific word. That means this word, WN1, is sampled from a multinomial distribution, which is parameterized by let me use beta to represent the word distributions beta 2. Then I got my first word the. And how do we sample the next word, right? William, right? Same thing, right? First, I need to determine what's the topic for this word, right? So if we denote the topic index by ZN2, right? Meaning that's the nth document second word, right? I'm gonna sample ZN2 from my multinomial distribution parameterized by topics mixtures data again, right? And according to ZN2, maybe this time my ZN2 is the third topic, right? 0, 0, 1, 0, right? So then I'm gonna pick up the corresponding topic distribution or word distribution, which could be beta 3, right? So then your William is actually sampled from a multinomial distribution parameterized by beta 3. Right? And you just keep doing this until you generate the last word, I guess is 2. Right? Does it make sense? This is the whole sampling procedure. Right? Again, this is a very, very simplified procedure. This is very, very different from how human beings compose this paragraph, right? But again, such a simplified probabilistic model in many practical scenarios is enough to extract those keywords, topic words. So here I want to emphasize that the word distribution, namely topic, like topic K, is a multinomial distribution, is probability vector over the entire dictionary of the words, right? And the topic mixture for every document is another multinomial distribution, is also a probability vector, the summation is 1. And for convenience, right, the topic index for each word, like Z and J, meaning that the jth word, the topic of the jth word in document N, right, is represented by a 1-hot encoding, right? And because we assume there are k topics, so the k by 1-hot vector, like there only one entry is 1, indicating the topic index, all the other elements are simply 0, right? And here W and J is the actual word, the actual word in that document, the actual jth word in document N, right? For convenience, we're going to also use a 1-hot encoding to represent as well. So W and J, right? You can view it as a 0, 0, 1, 0, 0, 0, 0, something like that, right? And it contains the elements, is the total number of the document, total number of the words, right? So the non-zero entry corresponds to the index of the actual word. Right? Does it make sense? And how do we sample each word distribution for the topic? Right? Now we need to recall what we have discussed before. Right? We mentioned that if we want to sample a distribution of k items, right? What kind of distribution can we use? Right? If you want to sample the probability vector for multinomial distribution, the random variable now is a probability vector, where the summation is 1. Itself represents a multinomial distribution. How do we sample such a distribution? It's a Dirichlet distribution, right? Dirichlet distribution is a distribution of distribution. Right? If you could remember, right? If you sample a variable, say from a Dirichlet distribution, see the parameters alpha, right? And suppose this alpha is k-dimensional, then theta will be a probability vector, right? See the 1, see the 2, see the k will be a probability vector. and their summation is 1. Right? So that means a sample of Dirichlet distribution will be a valid multinomial distribution. Okay? That's the benefit of Dirichlet distribution. So here we use Dirichlet distribution or Dirichlet prior distribution to sample both the word distribution for every topic and the topic mixture for every document. So the model becomes becomes clear. So here we assume there's a hyperprime eta, and we have a directly prior over the word distribution for every topic k, which we denote by beta k, right? Meaning that beta k is sampled by this directly distribution parameterized by eta. So this is a probability density of the prior directly distribution. Right? This is something we have the form we have discussed before, right? And then for each document, right, we need to first sample the topics mixture. Again, topic mixture essentially is a multinomial distribution as well, but it's just a k-dimensional multinomial distribution representing how likely what's the probability each word belongs to which topic, right? So we're going to use another directly prior distribution to sample each topic mixture theta n, right? Is parameterized by alpha, right? So this is a density of the directly distribution. So theta nk here means that the k's element in theta n. So remember, theta n is a vector, right? Theta n is vector. Theta n1 means that the first element in theta n, theta n2, second element in theta n, theta nk, the kth element in theta n. And this is a probability density of the Euclid distribution. And then, given theta n, right? Theta n is probability vector, multinomial distribution over the topics, right? So we're gonna sample every word topic, right? So the MJ, as we mentioned, right? We're gonna use a multinomial distribution to sample each CNJ given theta n, right? Theta n is a parameter of this multinomial distribution. And this is how we write down the probability of this multinomial distribution, right? It's theta nk, which is probability. You take k topic, right? To the power of znjk, because znjk means the k's element in this one hot including znj, right? So there's only one element which indicates the topic. And once we know znj, right? So suppose the case element is 1, we know that okay, it must be belongs to the k topic, right? And given the beta includes all the words distribution across the k topics, right? So we're gonna sample the actual word w and j following another multinomial distribution. And now this multinomial distribution is parameterized by topic k. Okay? And you write down the you write down the probability you sample this particular word w and j. Right? And for convenience, right, you can write down in the general form the probability of sampling w and j given the topic index z and j, which is one hot including, and all the topics, right, can be written in this way, right? This is a product across the topics, product over every word, right? You got a beta kv is actually the probability of the word we generated under topic k, right? This probability is chosen if both the topic that the word belongs to is k, right? Meaning z and j k is 1, and also the word itself is indeed v, right? This is just the Like otherwise it's simply zero. That means it's not this specific probability. So throughout this model, you can see that there are just two components. One is directly prior distribution to sample the word distribution and topic distribution. And then given the word distribution, topic distribution, just use multinomial to sample every word. And that's it. And because those beta keys and theta n's, right? The word distributions for topics and the topics mixtures, topic distributions for every document are all latent. Right? So that's why this model is called latent directly allocation, because you use directly distribution to sample latent random variables. I want to infer the posterior distribution of those latent random variables according to your observed actual words in your documents. Any question? Anyone feeling any uncomfortable about this modeling? Okay, yeah, I mean, if you're not get used to like you use a bunch of product over the probability elements to the power of those binary indicators, spend some time sitting down. I try to follow this. You will find this is a very, very convenient way to write that. Okay, and then according to this whole graphic model and also every conditional probability, right? We can write down the joint distribution of our model, which is over the word distribution across all K topics, the topic distribution for every document, the topic index for every word in every document, and every word in every document. Right. Of course, it's conditional on two hyperparameters. First is the hyperparameter in the directly prior that generates the word distribution on topics. And second is a hyperparameter alpha, which controls the directly prior distribution to sample the topics mixture for every document. Right? Conditional eta and alpha. Right? So you can see that first, this component using directly prior to sample the word distribution for every topic K, right? And this part go across M documents, big M documents, like conditional alpha, to use directly distribution to sample the topic distribution for every document. Right? And this part, right, is inside each document, right? So remember, so your product over M is here, right? So it's inside each document, right? You go over every word in each document. You first, according to topic distribution in this document, which is theta n, right? You sample the topic index for J word, every J word, right? Z and J, right? Then according to Z and J and topic, the word distribution, you sample the actual word W. But here, for convenience, because W and J is represented by this one hot encoding, right? 0, 0, 1, 0, something like that, right? That's why we can represent the likelihood in this form. Does it make sense? Right? Again, if you feel a little bit uncomfortable about the modern component, how we write in this way, it's totally normal, totally fine. Like just write down for 5 minutes, try to follow up this. Yeah. So it should be pretty straightforward. Okay, so this is our model. We have introduced the whole model framework, which gives actually a very simplified sampling procedure, which assume how those words are generated, right? And according to which we can write down the joint probability. Then what is the inference task? So our inference task mainly has two goals, right? First, given a collection of documents, remember each word in each document actually have already been observed. Like we know them. Right? We want to infer what are the word distribution for every topic, like beta 1 to beta k, and also what are the topic distribution for every document, right? Namely topic mixture. Also, we want to know what are the hyperparameters alpha and eta that controls the generation procedure. This is our task. And the problem is that you can try this, right? The true posterior is intractable to compute. Basically, you don't know what is the true posterior of the beta. What is the beta given your collection of document? Let me just write it as D, right? It's just collection of the words, right? You don't know what is the posterior, true posterior of the topic mixture, like given a collection of documents. You don't know that. Right? You won't be able to compute. Right? That's why we're gonna use the variational inference framework. So basically, we're gonna use the variational EM algorithm. In each step, we're gonna update my approximate posterior distribution about the topic word distribution, the topics mixture for every document, and the topic index for every word in every document. And in the M step, we maximize the variational lower bound with respect to the two hyperparameters alpha and eta. So this is the whole framework. And for ease of computation, we use the mean field assumption about the variational posterior approximation. So basically, we assume that the posterior of beta, theta, and z can be decomposed as the posterior of every word distribution for every topic k, and multiplying with every topic distribution q theta n, and every distribution over the distribution of the topic index over each word. So you can see that they are fully factorized, right? They're factorized over topics, they're factorized over documents, they're factorized over each word. Oh, z variable, because you also have a latent variable about which topic every word belongs to, right? One of what? Yeah. So this is also a categorical variable, right? This is a one-hot encoding. This is a k-dimensional one-hot encoding telling us which topic each word belongs to, right? And you know, when you know which topic this word belongs to, you can retrieve the corresponding word distribution and sample the actual word, right? So you need to know this ZNG as well. And here, like for convenience, we're gonna use this mean field variational approximation. We assume, okay, all those posterior are fully factorized. Any questions so far? Okay, then the remaining work is really mechanical. Nothing special. So we can start with updating each Q and Z, QZ and G, meaning I want to update the variational posterior of the topic index on every word, meaning in N's topic, in J's word, right? What is their topic index, right? So according to the mean field variational update, right, we know that we need to take a logarithm over all the conditional probabilities that contain this specific random variable Z and G, right? And then you take expectation under the posterior of all the other variables, right? You take exponential, you normalize, that's it, right? And then let us look at which probabilities that contain Z and J. So this is a drawing distribution, right? So although this seems complex, right? But if you look at a particular variable Z and J, right? We found out there are only two types of terms that involving Z and J. One is the prior for Z and J, given the topics matrix theta n, right? We sample Z and J. This is prior, right? And then given Z and J, how do we sample the corresponding word, right? So actually, you're only involving the terms here, right? You take a logarithm, right? This will give you this, right? This multinomial distribution, if you write it down, is something like that, right? So theta is like k from 1 to big K, and theta n k to the power of z n j k, something like this, right? This is multinomial distribution. So if you take a logarithm, you move z and j k in front of it, you have a logarithm of theta n k, right? And similarly, you got z and j k here, you take a logarithm, you're gonna move z and j k here, right? And you just take the common factor of the logarithm of these both terms. And inside this, you're gonna you turn the product into summation, and this log beta kv, you take expectation, and here WNGV is actually just the elements in your one-hot encoding, right? It's mostly just 0, right? And here, only related random variables are beta kv and theta and k, right? So be careful, this is random variables, right? There are elements in theta n and beta k, right? They're all random variables, so you need to take expectation of logarithm of them, right? Like suppose this can be computed, right? So we can see that the update is actually proportional to e to the power of summation z and j k, k's element of z and j, multiplying with this guy. So what does this correspond to? Which distribution does this correspond to? This just corresponds to another multinomial distribution. That's it. Right? How do we see that? Right? If you look at multinomial distribution in the general form, right? So suppose I got a z vector, it's not z and j here, and the parameter I have theta, right? So we know that the multinomial distribution will be something like this, right? Theta k to the power of zk, right? If you turn into some exponential form, it basically means, okay, you take exponential, then you take a logarithm over the above, right? If you take a logarithm over the above, right, your product becomes summation, your power will be moved in front of it. It's something like this, right? It's it'll be something like this from k to big K, and you have zk logarithm of theta k, right? So you can just extract who is multiplying with each zk and take exponential and take normalization. That's it. That's how you get your multinomial update of your directional posterior Q, Z, and J, and how do you determine the parameter of the multinomial update? Like, again, you just take exponential of this guy, and then you do normalization. So it's very simple. And you can apply the similar trick to update each Q theta n and each Q beta k. You will see that it will also be a Dirichlet distribution. What you need to do is just to update the parameters of Dirichlet distribution. So let's stop here today. We're gonna go through them on Thursday.